A good day to Miss Annin, and we are from Group 8, and we are going to tell about the case study about gear system design. Before that, let me introduce my teammates. Rukeshwan, son of Kali Selvan, Maxwellander Michael, Fu Chuan Sun, and myself, Derek, son of Desmond. And I'm going to talk about the introduction for this case study. So the first of all, arithmetic and geometric sequences are important mathematical concepts with many real-life applications, especially in engineering and infrastructure planning. In bright lighting systems, proper spacing of lampposts is essential to ensure uniform illumination, safety, and cost efficiency. This case studies applies arithmetic and geometric sequences to model two different street light spacing plans on a bridge. By using an arithmetic sequence with a constant increase in distance and a geometric sequence with a constant percentage increase, the study demonstrates how these mathematical patterns can be used to solve practical problems and support better decision making in real world applications. That's all from me. Thank you.
Good morning everyone, my name is Maxwellander Michael, and now I will be presenting about the case study statement which is the gear system design. A mechanical engineer designs gear teeth distribution. In the first design, the number of teeth increases by 5 for each gear. The first gear has 20 teeth, arithmetic sequence. In the second design, the number of teeth increases by 10% per gear. The first gear also has 20 teeth, geometric sequence. Next, I will be presenting about the fila table. In this fila table, there are 4 components. The first one is facts, ideas, learning issues, and action plans, and also resources needed. So the first fact in this fila table is that a mechanical engineer is designing a gear system. Second, the system consists of several gears arranged in order. Third, the first gear has 20 teeth. Fourth, in the first design, the number of teeth increases by 5 for each gear. And the last facts, in the second design, the number of teeth increases by 10% for each gear. Next, for ideas, the first ideas is that the change in the number of teeth follows a pattern. Second, the first design can be modeled using an arithmetic sequence. Third, the second design can be modeled using a geometric sequence. And the last ideas, mathematical formulas can be used to predict the number of teeth in any gear. For the learning issues, the first one is that how to identify an arithmetic and geometric sequence from real-life situation. Second, how to write the formula in the nth term for each sequence. Third, how to calculate the total number of teeth in a given number of 4 gears. And the last one is that how gear design affects mechanical performance. For the action plan, first, determine the type of sequence for each design. Second, write the correct formula for the number of teeth in the nth gear. Third, apply the sum formula to find the total number of teeth in the first 10 gears. And the last one, compare both designs to understand their difference. That's all from me. Thank you.
Okay, today I'm going to explain manual solution in my case study. Okay, the scenario is a mechanical engineer design gear teeth distribution. In the first design, the number of teeth increases by 5 for each gear. The first gear has 20 teeth, is shown clearly arithmetic sequence, and in the second design, the number of teeth increases by 10% per gear. The first gear also has 20 teeth, so it's also shown clearly geometric sequence. Okay, now we go through about task. Okay, task 1 is write the formula for the number of teeth in the nth gear for both design. The second task is calculate the total number of teeth in the first 10 gears for both design. Okay, for manual solution for task 1, which is arithmetic sequence and geometric sequence, for calculate the formula of the number teeth in the gear, so we can use Tn equals to A plus N minus 1 times with D. The second one is Tn equal to AR power of N minus 1. Okay, A is first term, n is total and d is a common difference. So the first term is 20, is shown clearly. Okay, the second one is d. The different ratio is the common difference is 5 because it increases 5 by 5, 20, 25, 30, 35 like that. So for first design, you just substitute the value arithmetic sequence using formula Tn equal to a plus n minus 1 times with t. So 20 plus n minus 1 times with v times with 5. That's all for design 1. For design 2, geometry sequence, so Tn equals to ar power of n minus 1. So you substitute 20 value into a, so 20 times with 1.1 power of n minus 1. Okay, how I can get the answer 1.1? Okay, for common ratio you should do 10 percentage, right? So 10 percentage times with 100, then plus with 1, so you get answer 1.1. No solution task 2. So the total number of teeth in the first 10 gears, use formula Sn. So first design arithmetic sequence, right? For sum, you can use formula Sn equal to n per 2 to a plus n minus 1 times with d. So just substitute the value. A is 20, 10 is n is 10, so d is 5. So you get total sum of teeth for first design is 425. The second one is design 2, geometric sequence. So formula of sum. So you can use the formula Sn equal to a r power of n minus 1 divided by r minus 1. So substitute the value. So you get answer 318.74. So the total teeth in first 10 gear for design 1 is 425. The second design is 318.74. Okay, next the comparison with Excel solution. Okay, what the difference with manual and take Excel? So manual is we do a manual, we write the number and substitute into the formula. But for table Excel, you just insert the value. The Excel will automatically calculate the value of arithmetic and geometric. For example, n1. So you just insert the value in one table using the formula. So the arithmetic solution will calculate automatically. So its table calculation is more easy when compared with manual. For geometry also same. So you substitute the value. You just insert the value in the column n 1 until 10. So you substitute the value, for example 9. So you substitute the value, insert the value 9. So the geometry xn value is automatically calculated. But for my opinion, I will prefer to manual because for example 10. So 10 total is 10. So I can directly substitute the 10 into formula using Sn value, using Sn formula for arithmetic and geometric. I substitute the 10 into the formula n. So I automatically get the answer directly. So I no need to use Excel one by one. I type the answer. I insert the value of n until 110. So that is a difference using manual and table Excel. So that's all from me. Thank you.
Okay, for the conclusion, in this case study, the gear teeth distribution problem was successfully analyzed using both arithmetic and geometric sequence. The first design followed an arithmetic sequence where the number of teeth increased by constant value of 5 for each gear. Starting from 20 teeth, the second design followed a geometric sequence in which the number of teeth increased by 10% per gear, also beginning with 20 teeth. Mathematical formulas for the number of teeth in the n gears were derived correctly for both designs. The total number of teeth for the first 10 gears was then calculated using the appropriate summation formulas. The arithmetic design resulted in a higher total number of teeth compared to the geometric design, indicating a linear growth pattern versus a percentage-based growth pattern. This case study demonstrated how different mathematical sequences can be applied to real engineering design, and how the choice of sequence affects the overall system outcome. The use of arithmetic and geometric sequence provide engineers with useful tools of planning, predicting, and optimizing mechanical designs such as gear systems. Alright, next, for the reflection. Through this case study, we can understand that how arithmetic and geometric sequence are applied in real-world engineering problems. We learn how to translate a particular engineering scenarios into mathematical expressions and how to choose the correct formula based on the type of sequence involved. This activity also improves our problem-solving skill, especially in identifying key information such as the first term, common difference, and common ratio. Additionally, verify the manual calculation using Excel, enhance our digital skills, and increase our confidence in checking the accuracy of mathematical results. From a teamwork perspective, this project helped us improve communication and collaboration within the group. Each member contributed to different parts of the task, such as calculation, verification, and report writing. Overall, this case study strengthened our understanding of technical mathematics and highlight its importance in engineering applications.